In this part of the lesson, we are going to talk about continuity. Here's a definition of continuity. A function f is continuous at the point x equals a if all three of these conditions are met. One, f of a exists, which means if you plug in x equals to a into the function, then the output at a exists. Two, the limit as x approaches a of f of x exists. So remember the definition of a limit. For a limit to exist, the limit as x approaches a from the right is equal to the limit as x approaches a from the left, and they both equal to the same value. So we have to check both of these to see does a limit exist. And then finally is the limit. So the value from part 2, is it equal to f of a, the value from part 1? So is the limit as x approaches a of f of x equal to f of a? Because remember, this can happen. You can have this function, for example, as x approaches a from the left, the limit is going to be L because the graph is approaching L. As x approaches a from the right, so let's say this is a, the limit is going to be once again L. So the limit as x approaches a of f of x is going to be L from the left and right. The limit is going to be L both ways. However, f of a could be some number down here. And so the limit as x approaches a of f of x is not equal to f of a. That can happen. So in this case, this function is not continuous. Okay, so we have to check all three of these conditions. Here's an example. Is the function f given by f of x equal to x squared minus 9 continuous at x equal to 3? Why or why not? Now, anytime we're asked this question, is the function continuous, we have to go through all three of these requirements and show one by one that all the requirements are met. And definitely know these for the exam because this will 100% be on the exam. So let's go through all the requirements. 1, f of a has to exist. Okay, so f of a, our a value is 3 because we're saying is it continuous at x equals 3? That's our a value. So if I plug in f of 3, I get 3 squared minus 9. That's 9 minus 9, or 0. So that's good. That exists. 2, what is the limit as x approaches a of f of x? Okay, so in other words, we are trying to figure out what is the limit as x approaches 3. Remember, the a value is 3 of f of x, which is x squared minus 9. Now we learned in the previous video that for any rational function, limit as x approaches a of f of x is equal to f of a. So we just plug in a if we have a rational function, which we do. So this will equal to 3 squared minus 9, which once again is going to be 0. Now, just to show you guys that graphically, so we did this algebraically, just to show you guys graphically what that looks like, let's go ahead and graph this function x squared minus 9. So I'm going to go to Desmos, and you don't have to do this. I'm just showing you guys so you can see what it looks like. We got f of x equals to x squared minus 9. And as x approaches our a value, which is 3, from the left, coming from the left, the function behaves like this, and then coming from the right, the function behaves like this, but they're both approaching the same value, which is 0. So the limit does exist. Okay, and then lastly, we want to figure out, is the limit as x approaches a of f of x equal to f of a? So from part 2, the limit as x approaches a of f of x is equal to 0. From the part A, or from the first part, the limit f of a is equal to 0. So 0 equals to 0, they're the same. So all three conditions have been met, and this function is continuous at the point x equals to 3. Okay, so always go through these three conditions to show continuity. Now, when you get to piecewise functions, it's going to be a little more interesting. All right, so first let's just understand what's going on. G of x is split up into two different functions depending on what the domain is. So when the x values are less than -2, we're going to use this function to evaluate. When x is greater than or equal to -2, we're going to use this function to evaluate. So what I usually do, and you don't have to do it this way, but here's what I usually do. I make a number line, and I split up the number line into these two intervals. So here's my -2. Okay, now if x is less than -2, so this interval here represents, and it keeps going, x less than -2. If x is less than -2, which function am I using? I'm using the function 1/2 x plus 3. Okay, I'm using the function 1/2 x plus 3 if x is less than -2. Now what happens if x is greater than or equal to -2? So greater than or equal to, it means -2 or greater. So if x is greater than or equal to -2, then we're going to be using a completely different function. Okay, so on this side, when x is greater than or equal to -2, so for this domain, our function is going to be x minus 1. So that's kind of what's going on, right? So let's go through and check all three of the conditions based on this. Okay, number 1, does f of a exist? Now our a value is -2. We're trying to figure out is x continuous at -2, or f of x continuous at -2. So first we want to figure out what is f of -2 equal to. So f of -2, it means you want to evaluate the function, or I'm sorry, this is g, not f. Okay, we want to evaluate the function g at -2. So we got to figure out at -2, am I using this function 1/2 x plus 3, or am I using this function x minus 2? So remember, when the x value is -2 or higher, we're going to use x minus 1. So at x equals -2, it's going to be this interval, -2 or higher. So we're going to use a function x minus 1. So this will be -2 minus 1, which is going to be -3. So does g of a exist? Yeah, it exists. It equals to -3. Secondly, let's check, is the limit as x approaches a from the right of g of x equal to the limit as x approaches a from the left of g of x? Is that true? So let's calculate both of these things. Okay, so I'm going to make a little like rectangle here, and on the left of the rectangle, I'm going to calculate the limit. My a value is -2, so my limit as x approaches 2 of g of x. Now, which function do I use? That's the key value here. We are approaching -2 from the right in the first case. Okay, we want to have x approaches -2 from the right. So if I'm coming from the right, if I'm coming from positive infinity, which function am I using? Coming from the right, I'm using this function x minus 1. This is where the number line helps. Coming from the right, I'm using this function x minus 1. So if I plug this in, I'm going to get -2 minus 1, which is -3. So the limit as x approaches -2 from the right is going to equal to -3. Okay, now let's find the limit as x approaches -2, but coming from the left. Coming from the left, we're coming from, so coming from the left, we're coming from negative infinity. So which function do I use coming from negative infinity? I'm going to use 1/2 x plus 3. So if I plug in -2, I'm going to get 1/2 times -2 plus 3. So the 2 and -2, these reduce to be 1, so we get 1 times -1, which is -1 plus 3, and that's going to be 2. So what's happening? The limit as x approaches -2 from the right, coming this way, is equal to -3. The limit as x approaches -2 from the left, this is equal to positive 2. So the limit doesn't exist because from left and right, we're not getting the same value. Just to show you guys graphically what's going on, I'm going to go ahead and graph both of these functions just to show you guys that the limit, in fact, does not exist. Okay, so here are my two functions. I have f of x equals to 1/2 x plus 3, but my domain is restricted, so I'm going to put a squiggly bracket, and I'm going to put x less than -2. Okay, then I have f of x equals to x minus 1. Once again, my domain is restricted, and that domain is going to be x greater than or equal to negative 2. So look what's happening. Coming from the left, my function is approaching 2. Coming from the right, my function is approaching negative 3. So we can see here that it's not continuous. It's not a smooth, straight curve or line. There's a jump going on. So this function clearly from the graph, we can tell it's not continuous. So here we're going to say that the function is not continuous. And if you ever have a doubt, you can quickly just sketch a graph and check that. So the next example we are going to work on in class, you can try to do it on your own, go through all three conditions, check to see are they met. I'll help you guys get started. So now we want to check, is it continuous at x equals to 2? So if x is less than 2, okay, so if x is 2 or less, we're going to use a function 3x minus 5. If x is greater than or equal to 2, so if x is greater than or equal to 2, so if it's like this, then we're going to use a function 2x plus 1. So coming from the right, we're using 2x plus 1. Coming from the left, we're using 3x minus 5. So check all of these for continuity, and we will go over this in class. Same thing for the next two. So we want to check. We want to determine which of the following rules for continuity is violated at x equals negative 1. We will do these in class, but do think about them.